And this is 3.7, which is implicit differentiation. This is the alpha lesson. So in the textbook, I'm on page 157, and I'm going to begin here on the PDF. So the chain rule is what you did. This is an application of the chain rule. You need to connect what we do here with the chain rule. Are we good? So the chain rule I can think of as the derivative with respect to x of anything, or something with a y in it, is a derivative with respect to y times dy dx, because these dy's would reduce. And you'll see how that works out in example 2. Hopefully you see it. Or example 1. So I'm looking at example 1. And there's a picture in your book, okay? And the picture's at the bottom of page 157, but I reproduced the picture here. And the graph is x equals y squared. Well, it's not a function. It fails the vertical line test. Yes? But it still has a slope. The curve still has a slope. So how could we find it? Well, first off, I drew the picture. How did I draw it? I wrote y equals x squared, didn't turn it on, and asked the calculator to draw the inverse. Because the inverse function means x goes to y goes to x, and that's what this picture is in your book. So the equation is y squared equals x, and I want to take the derivative of both sides. So if I take the derivative, ready? I'm going to write this over here. This is just the left side. The derivative with respect to x of y squared. These letters don't match. Because they don't match, I have to take the derivative with respect to y and multiply that by dy dx. This is the chain rule. This is dimensional analysis. They would reduce. So the derivative of this thing with respect to y would be 2y. It's the power rule. Times this dy dx. The derivative of the right side, derivative of x with respect to x, is just a 1. What does that mean? It's a line y equals x. What's the slope of that? Slope would be 1. Power rule. This is what? X to the first. You have 1x to the 0. Anything to the 0 power is 1. To get dy dx by itself, we divide both sides by 2y. Well, now what do you have? You have something you're not used to seeing. In my table, I have x, y, dy dx equals, in this case, 1 over 2y. The derivative depends upon the y value. You're not used to seeing that. You're used to seeing the derivative depend upon the input, upon the x value. But in this particular problem, it depends upon the height. So here's what we did. We go to a couple points. I don't remember if they told us about these points. So there's a picture in the book, yes. So they go to the point 4, 2. So if 4 is your input, look what happens. You go 4 to the right. Because it's not a function, you have 2 outputs. Up 2, down 2. 4 2's on the curve, 4 negative 2's on the curve. Well, think what happens. The slope has to depend upon y here, because this slope up here is positive and that's negative. They don't have the same slope. So what's going on? It's 1 over 2y. This y is 2. That slope's 1/4. This slope's negative 2. That slope's negative 1/4. So here's the equation of the tangent line. So we're just going to take a step back from this and make sure you can understand what you're doing, because it's 100% consistent with what you've been doing. So if I go back here, I don't like to keep erasing this thing, but there's no room because Winnie has to have her birthday on Sunday, so we have to put that on the board. So there's not enough room to write up there. If we back up to something we're familiar with, make sure you understand this. The most user-friendly parent graph is y equals x. The next most user-friendly parent graph would be y equals x squared. So let's look at that. I have x, y equals x squared, and dy dx would equal 2x. Yes, that makes sense to me. Okay? But that is a function. It passes the vertical line test. So if I put a 4 in here, if I go 4 to the right, you would go up 16 on the curve. And the slope would be an 8. And the parent graph of the tangent line, the pre-image, would be y equals 8x. And the slide would be 4 to the right up 16. So the tangent line would be y take away 16 equals 8 times x take away 4. Yes, that's a pretty user-friendly question. But this is the same thing, except it wasn't a function, but the process is the same. Ready? We found the slope. In this case, when x is 4, because it's not a function, there's 2 outputs. So we have 2 different slopes. This is the slope in the first quadrant. That's the slope in the fourth quadrant. But the tangent lines are done the same way. Here's the slope. Here's the magnitude of the slide. Do the opposite to x, do the opposite to y. Same thing down here. So when you are confused, when you're struggling for this, back up to something you get. And the most user-friendly thing to back up to would be y equals x squared. And then you just say, I'm going to take what I did for y equals x squared and apply it to the problem you have. Okay? So that's up there. That's your model. And you're going to go to problem number 3. All right, now I forgot there was in the recording. So if we back up in the book, to the derivative notation, which is on page 101. Okay? On page 101, they write 4 different ways at the top of the page to express the derivative. And, people just, oh, that's, there's no problem there. I'm not going to pay attention to that. This is what we're trying to find out. The change in the height with respect to the change horizontally. That's what the derivative means. The change in the height with respect to your x, because you're going left and right, and you wonder how much the height is changing. Okay? So in this problem, you've got the implicit differentiation on the left. You've got the quotient rule on the right. The rest of it's algebra. But here, you see that the slope of the curve depends upon x and y. right? So, like we could put a number in here. Like if you put 2 in here, ready? You would get 1/3. 1/3 equals y squared. So what's y? Y equals square root of 1/3. Well, we didn't come up with a really good example, but at that time, then you would put in 1 and root square root of 1/3 in here, and that would give you the slope. It's kind of a sloppy example. Example 2. Now on example 2, there is a picture in your book on page 158. It's the unit circle under a size change of magnitude 5. So instead of having x squared plus y squared equals 1 squared, you have x squared plus y squared equals 5 squared. It's a size change. But we want to find the slope. So you would get this. You're taking the derivative with respect to x of the right side. And the derivative of the sum is the sum of the derivatives. This letter matches that letter. You just get a 2x. This we just did. This would be 2y dy dx. Derivative of a constant is 0. Now what? We want to get dy. That's what we're trying to find, dy dx. So we undo what's been done to that in reverse order of operations. So we undo the addition first. We add a negative 2x to both sides. Then we divide both sides by 2y. The 2's reduce. The derivative is negative x over y. Well, think about that. That makes sense because the picture in the book, they're looking on the point 3, negative 4. So I'd say, okay, on the circle is the point 3, negative 4. Our work is the derivative with respect to x is the opposite of x over y. So our slope there is going to be the opposite. It's going to be a positive 3/4. Yes? So that means the tangent line right there, the pre-image, would be y equals 3/4 x. The slide is 3 to the right down 4. The image would be y plus 4 equals 3/4 x take away 3. That's the tangent line to the circle at the point 3, negative 4 in quadrant 4. And you see the picture of it, the red tangent line. It has a positive slope. Because it was the opposite of x over y. Okay? Now, you're going to 11. I want to caution you about something. 11, I did it the long way, but you can do 11 by comparing it to this. There's a shortcut to 11. If you put your pencil down for 30 seconds and read 11, that could save you 2 minutes worth of work, maybe more than 2 minutes. So here's 11. Chain rule, the derivative of this, power rule, 2 times mu d mu. But derivative of what's inside is a 1. 2 times this, derivative of what's inside with respect to x is dy dx, and on that side it's a 0. So we're getting rid of this addition, then we're getting rid of that multiplication, and we quantify it there. But the right side differentiated to 0 in both problems. Yes, I remember that. So look what happened. Instead of the slope being negative x over y, the slope was the magnitude of the slide. Replace x with x take away 1. Replace y with y, take away 1. It's the opposite of that, and that's your derivative. So all this work, it takes you to the same answer. As if you just recognized this thing got slid 2 to the right, 1 to the right, up 1, by doing the opposite. So you do the opposite to the pre-image, which was the slope in the example. And you would get the slope of the circle that's undergone the transformation. All right? Now, what's going to happen is we're just going to show you example 3. We're not doing the problem that's connected with that. So as soon as we show this to you, the children at home are dismissed to do the exit ticket. And then we will see you on Monday. And when I say here, it says refer to the PowerPoint or page 158. Here's the work for example 3. Find the slope that's defined at every point. 2y plus this mess. What do I get? The derivative with respect to x of this would be 2 dy dx. Derivative of x squared is 2x. The derivative with respect to x of sine y would be cosine y dy dx. If it was derivative with respect to x of sine x, it would be cosine x. Because these letters don't match up, it would be cosine y dy dx. Get all the dy dx's to the left. What do you end up with? This. Why does that matter? Because the cosine only has defined between the range is from -1 to 1. So the only thing that makes this undefined would be 0 in the denominator. You can't get a 0 in the denominator. So then they're telling you it's defined for all points, because you couldn't make the denominator 0 when you differentiate it. So the people that are at home, that's it for the alpha lesson.